Today we're going to talk about parametric differentiation formulas. If x and y are both differentiable functions of t, and if dx dt does not equal 0, then the derivative of y with respect to x equals dy over dt. So the derivative of y with respect to t, this is parametric, over the derivative of x with respect to t. And if we were to multiply both of these by dt, they would both cancel out, and we would just end up with dy over dx. Now, the second derivative, we have if y prime equals dy dx is also a differentiable function of t, then the second derivative is really the derivative of the first derivative. And that's really what second derivative is. But it's a little strange when you work with parametrics. It's the derivative of y prime with respect to t over dx dt, and that's the second derivative. This is saying the derivative of the first derivative, which is what we normally think of as the second derivative. We'll talk more about that in a little bit, especially when we do inflection points on letter C. In example 2, we have analyzing a parametric curve. Consider the curve defined parametrically by x equals t squared minus 5 and y equals 2 sine t. Remember, we're only going from 0 to pi. Now, I looked at this one, and I thought, well, if I'm going to plug radian measurements into t squared, I'm certainly going to get a decimal value. And if I went from -2 to 2, well, we can't do that. Let's say 0 to 2 or 0 to 3.14 using integers, I'm going to get decimal for sine of t. So either way on this one, we're going to get decimals as an answer. So I thought, well, let's just use our calculator for this one. So I'm going to open up the calculator. Turn that on at this one right here, and let's get the calculator pop back up here. Here's how we graph parametric equations. We turn the mode to parametric. Then I can quit out of that. If you go to y equals now, it has x sub 1 of t, y sub 1 of t. And so we're going to put in for x t squared minus 5. And for y, we're going to put in 2 sine of t. And then I'm going to go to window and make sure I'm going from 0 to pi. The step is reasonably small. And it even says, and the calculator is going to disappear, but from -7 to 7, that's the x. From -4 to 4, that's the y. So when we go to window, I want to go from -7 to 7. By a scale of 1 is fine. -4 to 4. And I should have a scale of 1 also. So here we go. We're going to graph it. And that's what it looks like. So, if you're going to do this, and if this is a calculator part of the test, letter A, we would just draw a rough sketch of this. Let's see, it's at 1, 2, 3, 4, 5. It's back here at about 1, 2, 1, 2, 1, 2, 3, 4, 5. Somewhere right here. Then it goes up to somewhere past 1. So it's looking something like that. And we have the direction that it was graphed. And letter B says find the highest point on the curve. Well, the highest point of the curve, I don't know, is maybe somewhere here. I'm just guessing. But the slope of the tangent line would be 0 at the highest point. So if you look at the derivative, we have dy over dx with respect to t will be 2 cosine of t over 2t. Now remember, t is going from 0 to pi, so we always have to keep that in mind. In order to make, now we want this equal to 0 because the slope of the tangent line is 0, of course. Now in order to make a fraction 0, we just have to make the top equal to 0. So we have cosine of t equals 0 when dividing by 2. And we know that cosine is 0 at pi over 2. It does say justify your answer. And we're going to show that the derivative does go from positive to negative. Here's our number line. Here's pi over 2. Now, remember, we're only going from 0 to pi, which means all our t values are going to be positive. So now I really don't have to look at the denominator because the denominator is always going to be positive. And that's not going to change the sign of our values. So if we look at pi over 4 and 3 pi over 4 for cosine, cosine is positive at pi over 4, and then it's negative at 3 pi over 4. So the curve is going up, and then it's coming down across pi over 2. So maximum, or let's say, how do they put it? Let me read that again. Find the highest point. So I'll say highest point is, well, I guess we got to plug pi over 2 in for the two values. It says find the highest point on the curve. The x is going to be pi over 2 squared minus 5. So pi squared over 4 minus 5. There's your x coordinate. And when you put pi over 2 in for 2 sine of t, you're going to get, well, just 2. So there's the highest point. How do I know that? The first derivative changes from positive to negative. And there we go. There's letter B. I'll put letter C off to the left over here. Find all points of inflection on the curve and justify your answer. We need to take the derivative of y prime with respect to t over dx dt. Well, let's look at what the first derivative was. Where did I write that? The first derivative is sitting right there, actually. 2 cosine of t over 2t. 2 cosine of t over 2t. And that's dy over dx. That's the first, excuse me, the first derivative. So we're going to take the derivative of this. Now, we can cancel out the 2's, make our derivative a little easier. So the derivative, this is actually y prime right here. The derivative of y prime is going to equal bottom times derivative of top minus top times derivative of bottom all over the bottom squared. Now that's actually dy dt, or the derivative of the first derivative, and that's over, this is where the confusing part comes in, that's actually over dx dt. So still you put it over the derivative of x, which is 2t. So the top is the derivative of the first derivative. This right here is the derivative of the first derivative. And then you put that over dx dt. That's how you find the second derivative using parametric equations. Now, can we, I don't think we can really, so we can simplify this a little bit. We have negative t sine of t minus cosine of t over 2t to the third. Now we're trying to, now that's the second derivative, there it is, and we're trying to find inflection points. So we want to know where the second derivative is equal to 0. So now I really have one function. So this really, the result is really not a parametric function. It's just a function. So when we go back into our calculator, I'm going to put the mode back to just function. In the y equals, I'll put in negative t sine of t, or in this case we're using x's because it's just one single function, minus cosine of x. And then I have divided by 2x to the third. Now the window, remember t is only from, or in this case we're using x's of course, the t is only from 0 to pi. And I missed. Let's try that. Clear pi. And we'll see if the y, now we're looking for where this is 0, so I don't really have to change my y min and max. If we graph this, let's see what we get. And there it finally crosses the x-axis. So now I can go to second, calculate. We're calculating a 0. Let me arrow over a little bit until we can see this cursor again. Should be coming up. Come on. Can we see it yet? There it is. Enter. Enter on the right. Take a guess. And when t is 2.798, so t equals 2.798 approximately. But it says find all points of inflection. So now I have to put 2.798 into the x and the y. I guess I can quit out of that. Let me see remind myself what the functions are. T squared minus 5, t squared minus 5, and I'm plugging this into 2 sine of t. So with our calculator, I'm going to take 2.798 and square that minus 5. There's the x value, and while I'm at it, I'll just take 2 sine of 2.798, and there's your y value. So 2.828, 2.829, 2.829. Oh, that stayed on there. That's strange. And 0.674. 0.674 is where we have a point of inflection on this curve. Arc length of a you can read it, curve. Let L be the length of a parametric curve that is transverse exactly once as t increases from t1 to t2. If the derivatives are continuous functions of t, then here we have integral from t1 to t2, and we're going to square root the square of the derivative of x and square the derivative of y. So let's look at the example we have here. Let's look at the derivatives first of all. Dx dt equals 3 cosine squared of t times, let's see, the derivative of cosine is negative sine of t. There's dx dt. dy dt equals 3 sine squared of t times cosine of t. Now look in the formula, these are both squared, so let's square each of these. I'll write it over here. We have 9 cosine to the 4th t times sine squared t, and this one is going to be 9 sine to the 4th t cosine squared t. So there they both are squared. Now we're going to integrate from 0 to 2 pi of the square root of these two things added together. Now they have, I don't think it really matters much, but they do have the x first, so we'll stay consistent. We'll do that as well. We have 9 cosine to the 4th of t sine squared t plus 9 sine to the 4th t cosine squared t. Well, we can factor out, let's see, what can we factor out? We can factor out a sine, well, let me write it. 0 to 2 pi square root of, between the cosines, I can factor out a cosine squared. Between the sine sines, I can factor out a sine squared. So I can take out a 9, of course, and I can take out a sine squared t plus cosine squared t out of each of those. And what's left in there, if I take a 9 out of the first one and a cosine squared, I'm left with a cosine squared t, and of course the sine squared is out of there. And then we have plus, the 9 is gone, a sine squared is gone, but we're left with the sine squared. We, of course, know the end over there, cosine squared t plus sine squared t has 1, so now it's times 1. And we have 9 sine squared t, oh, this isn't plus, that should be just times. Sine squared t, cosine squared t. And then we have, when we square root these, let me bring that up, we have 0 to 2 pi of 3 sine of t cosine of t. Of course, with this we're going to have the absolute value because we've just square rooted. And I should be writing the dt's with these. But if we look at the shape, and let's go to the book. The shape is off to the left here in figure 10.5, and notice that there's 4 parts to this asteroid. So rather than trying to compute all four pieces from 0 to 2 pi. In this case, we're just going to go from 0 to pi over 2, and from 0 to pi over 2 is the first quadrant. Both sine and cosine are both positive, so this allows us to remove the absolute value. And then since there's four pieces to this, once we get the answer to this, we're just going to multiply by 4, and it's a nice way to not have to deal with the absolute value. So we need to take the antiderivative of this. We'll let u equal sine of t, du equals cosine of t, dt. So I can pull the 3 out. So we have 3 integral of u, to pi, or u 0 to pi over 2 of just u. And cosine dt becomes du. Now I can integrate. So we have 3 times 1/2 u squared, which is really 3/2 u squared. And we can evaluate that from, well, let's just change. We'll put pi over 2 in for sine t. Sine of pi over 2 is 1. We'll put 0 in for sine, and that's 0. So really it's 0 to 1 now, and we don't have to resubstitute back in. So we have 3/2 times 1 minus 3/2 times 0. So we're looking at 3/2, but that was only 1/4 of the shape. Multiply by 4, and we end up with an answer of 6. Sketch the parametric equation, include direction, find the furthest left point. So we have, let's see, sketch the parametric equation. We're going from -2 to 3. So -2, -1, 0, 1, 2, and 3. That's the t, so we need the x's and the y's. So this is going to be 4 minus 4 is 0. 4 plus 4 is 8. That's 11. -1 in here. Well, I'm going to fast forward to save a little bit of time. There's the chart filled in. So we have 0, 11. That's a little bit off the map there. Right there. -1's 1, 2, 3, 4, 5, 6. 0, 3. 3, 2. 8, 3. And then this is shooting off to 15, 6. Whoop, direction is actually going that way as we graph this. We're finding the furthest point left. So we're trying to minimize the x coordinate. So we have dx over dt equals 2t plus 2. We're going to set that equal to 0. We're trying to minimize x. So we have -2 equals 2t, so t equals -1. Now we're going to show that that's actually, now when we plug -1 in, we get 6. So -1 is, I don't know, when t is -1, oh, x happens to be -1 when t is -1. That's why I was like, wow, that matches? Yeah, it actually does. So x equals -1 is the smallest x value. Now, if you put that on the number line, we have -1. Maybe we'll do, -2 and 0. If you plug -2 into the derivative for x, you get -4 plus 2. That's -2, so that's decreasing to -1. If you plug 0 into the derivative, you get 2, and now it's increasing. And that'll show that that is actually a minimum value. Given 4 cosine t, y equals 3 sine t, we write an equation of the tangent line to the curve at the point when t equals 3 pi over 4. So we have dx over dt equals -4 sine of t, and dy dt equals 3 cosine of t. So we have 3 cosine of t. I don't think I get much more than 20 minutes, so I'm going to have to do this in 2 parts.